Tollen's test. Tollen's reagent is a chemical reagent used to determine the presence of aldehydes and aromatic aldehyde functional groups, along with some alpha-hydroxy ketones which can tautomerize into aldehydes. The reagent consists of a solution of silver nitrate, ammonia, and some sodium hydroxide. It was named after its discoverer, the German chemist Bernhard Tollen. A positive test with Tollen's reagent is indicated by the precipitation of elemental silver, often producing a characteristic silver mirror on the inner surface of the reaction vessel. Mechanism of Tollen's test. Applications. Qualitative organic analysis. Once the presence of a carbonyl group has been identified using 2,4-dinitrophenyl hydrazine, Tollen's reagent can be used to distinguish ketone vs aldehyde. Tollen's reagent gives a negative test for most ketones, which alpha-hydroxy ketones being one exception. The test rests on the premise that aldehydes are more readily oxidized compared with ketones. This is due to the carbonyl containing carbon in aldehydes having an attached hydrogen. The diamine silver complex in the mixture is an oxidizing agent and is the essential reactant in Tollen's reagent. The test is generally carried out in a test tube in a warm water bath. In a positive test, the diamine silver complex oxidizes the aldehyde to a carboxylate ion and in the process is reduced to elemental silver and aqueous ammonia. The elemental silver precipitates out of solution, occasionally onto the inner surface of the reaction vessel, giving a characteristic silver mirror. The carboxylate ion on acidification will give its corresponding carboxylic acid. The carboxylic acid is not directly formed in the first place as the reaction takes place under alkaline conditions. The ionic equations for the overall reaction are shown below. Or refers to an alkyl group. Tollen's reagent can also be used to test for terminal alkynes. A white precipitate of the acetylide is formed in this case. Another test relies on reaction of the furfural with fluoroglycinol to produce a colored compound with high molar absorptivity. It also gives a positive test with hydrazones, alpha-hydroxy ketones, and 1,2-dicarbonyls. Both Tollen's reagent and Fehling's reagent give positive results with formic acid. Staining. In anatomic pathology, ammonical silver nitrate is used in the Fontana-Mason stain, which is a silver stain technique used to detect melanin, argon, dakin, and lipofuscin in tissue sections. Melanin and the other chromaffins reduce the silver nitrate to metallic silver. In silver mirroring, Tollen's reagent is also used to apply a silver mirror to glassware, for example, the inside of an insulated vacuum flask. The reducing agent is glucose. For such applications, clean glassware is required for a high-quality mirror. To increase the speed of deposition, the glass surface may be pre-treated with tin to chlorides stabilized in hydrochloric and hydrochloric acid solution. For applications requiring the highest optical quality, such as in telescope mirrors, the use of tin to chloride is problematic since it creates nanoscale roughness and reduces the reflectivity. Methods to produce telescope mirrors include additional additives to increase adhesion and film resilience, such as in Martin's method, which includes tartaric acid and ethanol. Fehling's test. Fehling's solution in a chemical reagent used to differentiate between water-soluble carbohydrate and ketone functional groups, and as a test for reducing sugars and non-reducing sugars supplementary to the Tollen's reagent test. The test was developed by German chemist Hermann von Fehling in 1849. This is the mechanism of Fehling's test applications. Fehling's solution is used to test for monosaccharides. The most important application is to detect reducing sugar like glucose. Excess of glucose in blood and urine can lead to diabetes. Fehling's reagent is also used in the breakdown of starch to glucose syrup and malto, maltodextrins, a polysaccharide used as a food additive. Hingeboard's reaction. The Hingeboard reaction is a test for the detection of primary, secondary, and tertiary amines. In this test, the amine is shaken well with Hingeboard reagent in the presence of aqueous alkali. A reagent containing an aqueous sodium hydroxide solution and benzene sulfonyl chloride is added to a substrate. A primary amine will form a soluble sulfonamide salt. Acidification of this salt then precipitates the sulfonamide of the primary amine. A secondary amine in the same reaction will directly form an insoluble sulfonamide. A tertiary amine will not react with the sulfonamide but is insoluble. After adding dilute acid, this insoluble amine is converted to a soluble ammonium salt. In this way, the reaction can distinguish between the three types of amines. Tertiary amines are able to react with benzene sulfonyl chloride under a variety of conditions. The test described above is not absolute. The Hingeboard test for amines is valid only when reaction speed, concentration, temperature, and solubility are taken into account. The Hingeboard reaction was first described by Oscar Hingeboard in 1890. Mechanism of Hingeboard reaction. Appel reaction. The Appel reaction is an organic reaction that converts alcohol into an alkyl chloride using triphenyl phosphine and carbon tetrachloride. The use of carbon tetrabromide or bromine as a halide source will yield alkyl bromides, whereas using carbon tetraiodide, methyl iodide, or iodine gives alkyl iodides. The reaction is credited to and named after Rolf Appel. It had, however, been described earlier. The use of this reaction is becoming less common due to carbonyl tetrachloride being restricted under the Montreal Protocol. This is a substitution reaction. Mechanism. Baeyer's Villiger oxidation. The Baeyer-Villiger oxidation is an organic reaction that forms an ester from a ketone or a electron from a cyclic ketone using peroxyacids or peroxides as the oxidant. The reaction is named after Adolf von Baeyer and Victor Villiger, who first reported the reaction in 1899. Mechanism of Baeyer's Villiger oxidation. Applications. Zooplatanol. Zooplatanol is a biologically active molecule that occurs naturally in the zeopetal plant, which has been used in Mexico to make a tea that can induce menstruation and labor. In 1981, Vinayak Kane and Donald Doyle reported a synthesis of zoapatanol. They used a Baeyer Villiger oxidation to make a lactone that served as a crucial building block that ultimately led to the synthesis of zoapatanol. Steroids. In 2013, Elena Swisdor reported the transformation of the steroid dihydroepiandrosterone to anti-cancer agent testosterone by use of a Baeyer-Villiger oxidation induced by fungus that produces Baeyer-Villiger monooxygenases. Cadiot Chodkiewicz coupling. The Cadiot Chodkiewicz coupling in organic chemistry is a coupling reaction between a terminal alkyne and a haloalkyne catalyzed by a copper-1 salt such as copper-1 bromide and an amine base. The reaction product is a 1,3-diene or dialkyne. This is a coupling reaction. The reaction mechanism involves deprotonation by base of the terminal alkyne proton followed by formation of a copper-1 acetylide. A cycle of oxidative addition and reductive elimination on the copper center then creates a new carbon-carbon bond. Applications. Unlike the related glacial coupling, the Cadiot-Chodkiewicz coupling proceeds selectively and will only couple the alkyne to the haloalkyne, giving a single product. By comparison, the glacial coupling would simply produce a distribution of all possible couplings. In one study, the Cadiot-Chodkiewicz coupling has been applied in the synthesis of acetylene macro cycles starting from cis-1,4-diethyl 1,4-dimethoxycyclohexa 2,5-diene. This compound is also the starting material for the dibromide through an bromosuccinimide and silver nitrate. The coupling reaction itself takes place in methanol with um, piperidine, the hydrochloric acid salt of hydroxylamine, and copper-1 bromide. Dakin reaction. The Dakin oxidation is an organic redox reaction in which an ortho or para hydroxylated phenyl aldehyde or ketone reacts with hydrogen peroxide in base to form a benzene diol and a carboxylate. Overall, the carbonyl group is oxidized and the hydrogen peroxide is reduced. The Dakin oxidation, which is closely related to the Baeyer-Villiger oxidation, is not to be confused with the Dakin-West reaction, though both are named after Henry Drysdale Dakin. This is an organic redox reaction. Mechanism of Dakin reaction. Applications. The Dakin oxidation is most commonly used to synthesize benzene diols and alkoxyphenols. Uh, Catechol, for example, is synthesized from ortho-hydroxy and ortho-alkoxyphenyl aldehydes and ketones and is used as a starting material for synthesis of several compounds, including the uh, uh, catecholamines, catecholamine derivatives, and 4-tertiary butyl catechol a common antioxidant and polymerization inhibitor. Other synthetically useful products of the Dakin oxidation include guaiacol, a precursor of several flavorants, hydroquinone, a common photograph depelling agent, and 2-tert-butyl 4-hydroxy anisole and 3-tert-butyl 4-hydroxy anisole, two antioxidants commonly used to preserve packed food. In addition, the Dakin oxidation is useful in the synthesis of indoliquinons, naturally occurring compounds that exhibit high antibiotic, antifungal, and anti-tumor activities. Eglinton reaction. In the related Eglinton reaction, two terminal alkynes are coupled directly by a copper-2 salt such as cupric acetate. The Eglinton reaction has been used to synthesize a number of fungal antibiotics and is important for carbon-carbon bond formation via the oxidative coupling of alkynes, as illustrated in this highly simplified scheme. This procedure was used in the synthesis of cyclooctadecanoline. Another example is the synthesis of diphenyl diacetylene from phenylacetylene. Applications. In 1882, Adolf von Baeyer used the method to synthesize indigo from 3,2-nitrophenyl propiolic acid. Shortly afterwards, Baeyer reported a different route to indigo, now known as the Baeyer-Drewsen indigo synthesis. Hay coupling. The Hay coupling is another variant of the Glaser coupling with the TMEDA complex of copper-1 chloride. An example is the coupling of trimethyl silyl acetylene. Favorskii reaction. The Favorskii reaction is an organic chemistry reaction between an alkyne and a carbonyl group under a basic condition. The reaction was discovered in the early 19th by the Russian chemists Alexei Grafovich Favorskii. When the carbonyl is an aldehyde, a rearrangement occurs and leads to an enone. When this rearrangement is catalyzed by an acid, it is called Mayer-Koster rearrangement. These are the applications of Favorskii reaction and mechanism. J-Walt reaction. The J-Walt reaction is an organic reaction involving the condensation of a ketone or aldehyde when R square is equal to H with the alpha cyanoester in the presence of elemental sulfur and base to give a polysubstituted 2-amino-thiophene. This is a ring forming reaction. The reaction is named after the German chemist called J-Walt. Mechanism of J-Walt reaction. Code-Itsuno reaction. The Code-Itsuno reduction, also known as the Code-Bakshi-Shibata reduction, is in a chemical reaction in which an achiral ketone is enantioselectively reduced to produce the corresponding chiral non-racemic alcohol. The oxazebolidine reagent, which mediates the enantioselective reduction of ketone, was previously developed by the laboratory of its own, and thus this transformation may more properly be called the Itsuno-Kode oxaborolidine reduction. This is an organic redox reaction. Mechanism of Kode-Itsuno reaction. Applications. Over the past couple of decades, the CBS reduction has gained significant synthetic utility in the synthesis of a significant number of natural products, including lactones, uh, terpenoids, alkaloids, steroids, and biotins. The enantiomer selective reduction has also been employed large-scale in industry. Jones it utilized the CBS reduction in the total synthesis of MK0417, a water-sulfur carbonic anhydrase inhibitor which has been used therapeutically to reduce intraocular pressure. A symmetrical reduction of a key bicyclic sulfone intermediate was accomplished with the CBS oxazeborolidine catalyst containing Me as the R- group. A symmetrical reduction of a 1,1,1 trichloro 2-keto compound in the first stage of the Code-link reaction for synthesis of amino acids and related structures with the choice of either natural or unnatural stereochemistry and various side chains. Asymmetrical reduction of 7 benzoxyheptone and 3,1 leads to S7 benzoyloxyheptane 1 and 3-ol, a chiral alcohol that leads directly to the synthesis of cannabinoids that are currently researched as enamide containing enol ethers but show potent inhibition of cancer cells. The selective formation of the chiral product is achieved by or CBS catalyst with the 89% yield and with 90% enantiomeric access. Jacobson epoxidation. The Jacobson epoxidation, sometimes also referred to a Jacobson Kartsky epoxidation, is a chemical reaction which allows enantioselective epoxidation of unfunctionalized alkyl and array substituted alkenes. It is complementary to the Sharpless epoxidation. The Jacobson epoxidation gains its stereoactivity from a C2 symmetric manganese 2 serine-like ligand which is used in catalytic amounts. The manganese atom transfers an oxygen atom from chlorine bleach or similar oxidant. The reaction is named after its inventor, Eric Jacobson, and sometimes also including uh, uh, Tsutomu Katsuki. Chiral directing catalysts are useful to organic chemists trying to control the stereochemistry of biologically active compounds and develop pure drugs. Several improved procedures have been developed. A general reaction scheme follows as mechanism of Jacobson epoxidation, carbonic fields reaction. In or in organophosphorus chemistry, the carbo the carbonic fields reaction is a three-component organic reaction forming alpha amino Methyl phosphonates from an amine, a carbonyl compound, and a dialkyl phosphonate. Aminophosphonates are synthetic targets of some importance as phosphorus analogous of alpha amino acids. The multi-component reaction was independently discovered by Martin Isra- Is- Israelevich Kab- Kabachnik and Elilsky fields in 1952. The reaction is very similar to the two-component Podwick reaction, which involves condensation of the phosphide and a performed imine. The first step in this reaction is the formation of an amine, followed by a hydrophosphorylation step where the phosphonate pH bond across the carbon-nitrogen double bond. The starting carbonyl component is usually an aldehyde and sometimes a ketone. The reaction can be accelerated with the combination of dehydrating reagent and Lewis acid. Enantioselective variants of the Kabachnik Fields reaction have been developed, for example, employing alpha-methyl benzylamine provides a chiral non-racemic alpha-amino phosphonate. Lucha reduction. The Lucha reduction is the selective organic reduction of alpha-beta unsaturated ketones to allyl allylic alcohols with sodium borohydride and lanthanide chlorides, mainly sodium chloride in methanol or ethanol. The Lucha reduction can be conducted uh, chemoselectivity toward ketone in the presence of aldehyde or toward alpha-beta unsaturated ketone in the presence of non-conjugated ketone. An enone forms an allylic alcohol in a 1,2 addition and the competing conjugate 1,4 addition is suppressed. The selective and the selectivity can be explained in terms of the HCAB theory. Carbonyl groups require hard nucleophiles for 1,2 addition. The hardness of the borohydride is increased by replacing hydride groups with alkoxide groups, a reaction catalyzed by the cerium salt by increasing the electrophilicity of the carbonyl group. This is selective for ketones because they are more Lewis basic. In one application, a ketone is selectively reduced in the presence of an aldehyde, actually in the presence of methanol as solvent. The aldehyde forms methoxyacetyl that is inactive in the reducing conditions.